All right, let's get into our new chapter, chapter 22. This will look at something a little bit different, but not too much. Okay. Chapter 22, what it's going to do is look at the chemistry of alpha carbons. Chemistry of alpha carbons. Okay, don't know what those are right now, but we will shortly. Okay, so we'll abbreviate with the Greek letter alpha most of the time. Okay, so let's see what our setup here is. Let's just look at part of a carbonyl molecule. All right, maybe something like that. Okay. So here's the carbonyl. We say that the carbon directly attached to the carbonyl is the alpha carbon. Okay. Pretty simple. And we say that the hydrogens are what? Alpha hydrogens. So once you identify the alpha carbon, you can see if there are any alpha hydrogens. Okay? This one has 3 of them. Okay? So we're going to be looking at the chemistry at the carbon right next to a carbonyl. Okay? So let's look at some real molecules like that. Okay, maybe these two to get started. How many alpha carbons does this one have? Okay. How many alpha hydrogens?
6.
Okay. So you want to be able to quickly identify those two things. What about this one down here? How many alpha carbons? 2. How many alpha hydrogens? 4 this time. Okay. So that's what we want to be looking at here. Okay. So the first thing we're going to look at with alpha carbons is this topic here, which the topic of tautomers. Tautomers. Anybody know what a tautomer is? Okay. Let's find out. Okay. Let's draw, for example, this carbonyl compound. Okay. Ethanol. And suppose we wanted to make the tautomer of it. Okay? So you can maybe write these things down so it helps you to remember. It's pretty simple. To write the tautomer, what I do is I convert the carbonyl to an OH. Okay. The double bond now goes between the carbonyl carbon and the alpha carbon. Okay. and then write in the hydrogens. So if you look, in a sense, one of these hydrogens here went up to that oxygen. So we go down by one hydrogen there. Okay. And these tautomers have names. The one with a carbonyl is called the keto-tautomer. And the one with the alcohol and double bond, that's called the enol tautomer. Okay? So you want to be able to identify keto and enol tautomers and draw them. All right? Let me give you some practice now. Okay, see if you can draw the enol tautomer for that one. And then try these other two. I'm going to draw the enol here, draw the keto down here. Okay, I'll call some people to the board, see what you got. Okay, who wants to come up and do this one here? Come on up. That's 3 carbons in there. It's 3 carbons in there. Erase. Good try. Anybody else want to come up? Okay. No harm in trying. You gave it a good try. You were close. Step by so everybody can see that. Is that right? Have a seat. Come on. Come on up.
What is the first name?
She beat you. We got a winner. We got a winner. All right. So here, okay, take a look. You have two alpha carbons, so I could have chose either side to draw the double bond. I can't do both sides. I just have to do one side. Okay? So she chose the right-hand side, which is fine, and then brought one of these hydrogens up there. Okay? Any questions on that? All right, since you're so anxious, why don't you come up and do this one? Your next green. Your next green. Yeah, isn't that easy? All right, so the same thing again. You have two alpha carbons, so I can draw the double bond on either side. She chose the right side, and then makes that the OH. Okay. Any questions on that? Okay, green. Okay, so this time we're going the other way. Let's see what she draws. Good job. Okay, so this time she noticed I have an OH, so that converts to the carbonyl. And here was the enol part, the double bond, and that converts to the single bond. Okay, these two double bonds just came along for the ride. Okay, any questions on that? Okay, let's talk about a couple other things about these tautomers. Okay, these things just don't happen by themselves. They need a little help. Okay, these things occur with either base and water or acid and water. Okay, so you put these things in one of those kinds of solutions, you end up getting a mixture of keto and enol tautomers. Okay? And it turns out to be an equilibrium mixture here. Okay? So these arrows get equilibrium arrows. Okay? And so here's the next important question is, all right, these things happen in acidic or basic solution. Which one occurs more, the enol or the ketone? Okay? The answer is the ketone. Okay? And it has to do with the carbonyl being a strong and stable bond. If molecules can form a carbonyl, the molecule likes that. It gains stability. Okay? Remember, it's stronger than the carbon-carbon double bond. Remember, it had the IR frequency of what? 1700. Carbon-carbon 1600. So it was a little bit stronger. Okay? So the keto exists more in solution than the enol. Okay? Typically, you're looking at around 98% to 2%, so very, very tiny amount of the enol. Okay? You might ask, is there ever a situation that I can get the enol to be more than the keto? Okay? Here, this one over here is an example. Okay? This one would exist more than this one. Anybody have an idea why? Because it's what kind of ring?
Aromatic.
Aromatic. Okay, so the aromatic ring tilts the scale so that that enol exists more. Okay, but other than that, all these others will have the keto beating the enol. Okay, because of that carbonyl. Any questions on that? Okay. Well, let's go down to number 3 on the outline. And spend the rest of our time on number 3. Okay. Here, we're going to look at an important topic called the enolate ion. The enolate ion. Okay. Let's come back to our original structure in class. Okay, remember we defined alpha carbon and alpha hydrogens using this thing. Okay. Well, here we're going to focus on an alpha hydrogen. Okay. And let's just look at it a little bit. Let's suppose we wanted to remove that alpha hydrogen. Okay, so if I wanted to remove an alpha hydrogen, I would need a base of some type to do that, which is called B there. And if that left, then these electrons would fall on the alpha carbon. Okay? So let's just draw what we would get from that kind of thing. Okay. So we would get that lone pair falling on the alpha carbon. Anything special about this thing here? What can we draw?
Resonance.
Draw a resonance, can't you? You got a lone pair adjacent to a pi bond. Okay? So we can move lone pair toward pi bond and have those go up to the oxygen. So you would get that resonance structure there. Okay? So here we get 2 resonance structures as a result of removing the alpha hydrogen. And these 2 resonance structures make up the conjugate base. What do you think the name of the conjugate base is? Hint. Hint. There it is. Yeah, I gave it to you. Okay? So these 2 resonance structures are called the enolate ions. Okay? So the enolate ions, draw it down, write it down, are those 2 resonance structures. Okay? Or you can put it another way, write it down. The enolate ion is what? The result of removing an alpha hydrogen. The enolate ion is the result of removing the alpha hydrogen. So that the enolate ion is the conjugate base. Okay. So this conjugate base has what? Resonance stabilization. Since it has resonance stabilization, what would you predict? That the alpha hydrogen is somewhat acidic. You might ask, how acidic is it? Well, look at the pKa value. It's not super acidic. Okay, so remember pKa's, water and alcohols, 15 to 16. It's not as acidic as that, it's higher up. These are around 20 or so. Okay? So we're going to need somewhat of a decent base to take those off, which we'll look at later. All right, well, with this under our belt, let's get some practice by drawing some of these. See if you can draw the enolate ion or acetone. Anybody want to come up and try this one? You volunteered, I volunteered.
Leave me on my face. Good job. Good job. You had that, didn't you?
Why do you volunteer? Okay, so again, you could take off either side, okay? Because both have alpha hydrogens. You took off the right-hand side, and then to get the resonance structure, came over here. Okay, any questions on that? All right, so let's take a step back here. And let's look at some bases to remove an alpha hydrogen. Okay? What bases are we going to look at in this chapter to do this? Okay? There's a few bases. One base would be the hydroxy ion, OH minus. Okay. Some other bases will be the methoxy ion, or the ethoxy ion. Okay. Those are some decent bases that could do it. And a third one that we're going to talk about here is something called LDA. Okay? Something we haven't seen before. Okay? So let's talk about LDA over here. What the world is LDA? Okay? Let me draw the structure for you. Okay? So LDA has this structure here. Okay? So how would we name that? Well, we name the metal part first. So that's lithium. Then I have these isopropyl groups on the nitrogen. So that's di-isopropyl. Okay. And then since you have alkyl groups on the nitrogen, that makes an amine. So we have lithium diisopropyl amine. And so those three letters is where we get LDA. Okay. So let's talk about its structure a little bit. Okay. If you look, you have lone pair on nitrogen, and it has a negative charge. Okay. Remember, amines were decent bases without a negative charge. Remember that? pKb's around 4. When I put a negative charge on the nitrogen, now it really gets to be a violent base. It wants to get rid of that negative charge. So this thing here is a pretty strong base, okay, because of that negative charge on nitrogen. Okay? So it's even stronger than these. These are negative charges on oxygen, which are decent bases. Put a negative charge on nitrogen, which is less electronegative, even stronger base. Okay, so that's the first characteristic. Second characteristic are these isopropyl groups. These have a lot of volume to them. Big, bulky. So here we have a bulky, strong base. What's one of the properties of a bulky, strong base? You got sterics. Let me give you some help. That's what I'm looking for. Okay, let's suppose we had acetone. Okay, so there's acetone. And suppose I react this with LDA. Okay? If you remember from aldehyde and ketone chemistry, we learned that this thing would love to attack the carbonyl. But will this thing get in there? No. Why? Because the bulkiness of it. Okay? These bulky groups prevent that. Okay? So that's why they make LDA like that, to prevent that reaction. You say, well, why would you want to prevent that reaction? Where else could it attack? The alpha hydrogen. Very good. Okay? So write it down. LDA only goes after the alpha hydrogen. Okay? So anytime you see LDA in a reaction, it's going to strip off an alpha hydrogen. All right, so let's look at some examples here. Okay, now what I want you to do is show the mechanism of attack to get the enolate on. Okay? Show how LDA attacks that molecule. And then you can try the second one. This takes away.
You want us to like draw the whole thing and like write instructions? I'll try.
Okay, sure, go on. Okay. Let's give you some help here, yeah, where's this? Put the hydrogen. Okay, good. We'll have to do this thing on the next exam. Now we're going on the board. Very good, good job. Any questions on that? Nothing new, now we're just showing the base. You want to do the next one, George? Yeah, just draw the arrow from LB8 here. No?
No.
Yeah, it's going right. There you go. There you go. There's no alpha hydrogen on the right-hand side, so we can't attack there. Good. Okay. Let me clean it up a little bit here. I know you meant this to be a carbon. Okay, so he rightfully attacked on this side because there's no alpha hydrogen here. We just had 3 methyls on it. Okay. Any questions on that? All right, so what we're going to do in the next lecture is make use of the enolate ion, okay? We're just doing this one step at a time because it gets cumbersome after a while. We know how to make this. Now what reaction can I do on this, okay? So we're just going to keep going along, okay? I'll see you guys on Monday.